All right, welcome everybody. Welcome to the round table, Eyes to the Sky, the next generation of large telescopes. Well, right now we are witnessing a golden age of astronomy and astrophysics. In recent years we have witnessed remarkable discoveries, like for instance the first direct detection of gravitational waves, or we have seen the first image of a black hole. So it's really an intense time, and the fact that within the past 15 years, 5 Nobel Prizes have gone to astronomy and astrophysics, I think shows how thriving this field really is. There are reasons for that. Astronomy is a highly technology-driven science. So it really relies on cutting-edge technology. And whenever frontiers in technology are being overcome, then it's basically certain that we will see new discoveries and that we will find out new exciting things about the cosmos. So this is what we're going to talk about today, how better and better telescopes bring us better and better understanding of the universe. And we will talk about how this works and why this is so exciting. So I'm Sibylle Ander. I'm head of the science department of the German newspaper Die Zeit in Hamburg. I'm also a trained astrophysicist, radio astronomer actually, and I'm very happy to welcome an exquisite panel of experts to discuss with today. So, to my right, Michael Kramer is director of the Max Planck Institute of Radio Astronomy in Bonn. So he is representing radio astronomy and instruments like the SKA or ALMA, so we are going to talk about this as well. Then there's David Reitze. He is executive director of the Laser Interferometer Gravitational-wave Observatory. Most of you may know it as LIGO. And a research professor at Caltech representing the exciting new field of gravitational wave astronomy. Welcome. Then we have Professor Linda Tacconi. She's research group leader in submillimeter interferometry and galaxy evolution at the Max Planck Institute for Extraterrestrial Physics in Garching, representing powerful ground-based ESO astronomy, among other things. And then finally we have Frank Steeds. He is COO and member of the board of managing directors of the Heraeus group, representing the industry side of high-precision astronomy. Welcome, everybody. So, Linda, you are also ESO Council President.
I was.
You were, but you were working on. You have influenced the buildup of many very powerful instruments that ESO is operating. Now ESO is planning to build a new record telescope, the 39-meter extremely large telescope. So why is it so important in astronomy and astrophysics to build larger and larger telescopes?
So that's a really good question. The answer I think you already gave. We've made a lot of discoveries, and with every discovery comes more questions. That's the fun part about science. And so we know that there are black holes. We know that we've now imaged one. But now we want to go further back into the universe and see the first black holes. We understand very little about the earliest black holes in the universe. We believe that they're one of the first things that may have formed, but we need to find them, we need to understand them. We also now know that there are thousands and thousands of extrasolar planets, so-called exoplanets, in our solar system. Some even in some of the nearest stars to our sun. But we need to understand, can some of those planets support life? That's going to take bigger and bigger telescopes at many different wavelengths. And so there's for every discovery, we have an order of magnitude more questions. And that's what keeps us going. But that's why we also need ever more powerful telescopes at all wavelengths.
Well, it's the biggest questions that we have, right? The questions for foreign life, the question for the history of the universe. And so, I think that's pretty convincing. Frank, at Heraeus, you are heavily involved in building all these instruments, also for ESO telescopes. You are doing many other things as well, so I would be interested in, is it particularly challenging to build instruments for astrophysics and astronomy as compared to jobs that you do for industry applications, for instance?
I think the maybe let me rephrase your question first. Yeah, you can ask yourself, I would say, why Heraeus is on that panel, or why I am on that panel. Yeah? Since we are a materials company and we are not astrophysics people, right? So, but we are doing fused silica, and fused silica is used in the telescopes for the optical elements. Yeah, that's why we are here, basically. Now to your question, is it different to work with industry or academia? I think the big difference is when you work with academia, you have a single project. And the single project, for that single project, you need to develop, for example, fused silica in a dedicated way. When you work with industry, usually you have a large volume of material that you can sell afterwards.
Okay, so but well, interaction-wise, so are scientists more well? Well, they have very specific ideas, I imagine. So is it complicated to work with scientists, or is it more fun, maybe?
So I would say in our organization we have scientists, and we have one here in the room working together with the scientific people. So they know each other and they can work together. And yes, of course, working with scientists is sometimes more challenging because of questions and so on compared to, let's say, R&D departments in industry. But let me point out an additional topic. We are at the very beginning of the value chain, making the material. You are using, at the end, the optical component, right? And in between, there are a number of companies shaping the lenses, coating the optical components. So it's always a set of companies working together with the scientific people.
Michael, you are one of the users of all these instruments as well. You are a radio astronomer, I was already saying this, and radio astronomy historically always has had the biggest telescopes. So this has some limits if you are only looking at single dish telescopes. So can you briefly explain how radio astronomy is creating ever bigger telescopes using more complicated technologies?
Yeah, in radio astronomy it's easy to combine the signals from different telescopes to actually synthesize a very big one. In fact, the separation of the telescope gives you the resolution as a big telescope of that size. And even now with intercontinental baselines, as we call them, or on satellites, we can connect these telescopes and form ever more telescopes. And of course, then we can also make more sensitivity by producing more and more smaller dishes and connecting them as well. You pay for this by a huge data rate. So some of the data rates we produce are the biggest in the world and will be for the time to come. So there are other challenges coming with that as well. But that's one way of getting ever bigger telescopes.
It's very complicated data processing, right? So we have seen this with the first image of the black hole, where the data processing really took months and years because you really have to be sure that you are getting the right picture. So is it one of the most complicated observational techniques? Is this fair to say? Interferometry?
I'm sure that my colleagues would say they have the more complicated. It's one technology that's actually now being used everywhere. I mean, we have LIGO, gravitational-wave interferometry, then we have the VLTI on ESO. So this is easier in radio astronomy actually, but the data rates that we get is actually the biggest problem. So for instance, for analyzing the image of the black hole, I mean, there was 1 week of data. That's a huge amount. And for the SKA, it will produce in 1 day more data than the whole humankind has produced in its past. And so we need to have new techniques. We cannot store these data, so we have to analyze them on the fly with AI and other clever things. So there is a lot of behind the instrument itself. It's not just the bare-bone metal or the optical. It's what you need to actually process the data to get it out of it. So in this sense, I think you're right.
Well, it's already, I think, an important point to understand that building bigger and bigger telescopes in astronomy and astrophysics means connecting different telescopes and creating virtual huge telescopes. And another interesting point is that this comes with a lot of data, right? So that modern astrophysics is really very close to all these other big data scientific fields and with its own challenges. So, well, this is really interesting, Professor Reitze. David, you are doing gravitational wave astronomy, and this is a really, really new field. I don't know, maybe somebody or some of you in the audience still remember the day when the first gravitational wave detection was announced. So it was detected in 2016, and well, scientists have been trying to detect them for many decades. So can you give us a very short introduction into what gravitational waves are, because, well, I think this is still something that is really hard to understand, how space-time can create waves. And can you also explain us briefly how we can detect them?
How much time do we have?
Well, I know that I'm asking for the impossible.
So briefly, what are gravitational waves? Well, they're a new way to look at the universe. They come out of Einstein's theory of general relativity. The short explanation is that when you look at light, when you have radio telescopes or optical telescopes, they're looking at charges moving around, oscillating around. We look at mass actually oscillating around. So I'm generating gravitational waves just by doing this. You can't detect them because they're so tiny. What they tell us, because when masses accelerate and move, and they imprint these gravitational waves that radiate out, is you can basically, if you have a detector that is sensitive enough to be able to detect the changes, and the changes that we're trying to detect are about 1/1000th, maybe even a little bit less than that, the diameter of a proton on Earth for a source that's maybe 500 million light years away. So you have to make really, really sensitive detectors, and we use the technique as Michael talked about, interferometry. So basically we take a laser beam, we split it into 2 equal parts, send it out each other at right angles, goes about 2.5 miles, 4 kilometers, hits a mirror, comes back, recombines. And as the gravitational wave passes actually through the detector, gravitational waves just go through everything. All right, it changes the time that light travels from the point of splitting in each arm in a very precise, known, and calculatable way. And as the light comes back, because the gravitational wave has basically altered the distance between those 2 arms, we can actually map it out. It's a transducer. So that's the idea basically. Of course, there's a lot of complexity behind it. We do use Heraeus glass. It's critical to our endeavors because it's the lowest absorption glass in the world. So yeah, we're basically trying. We've pushed this technology for a long way, and what we're trying to do now is look at a new sector of the universe that's not accessible to the electromagnetic spectrum.
Well, we will get back to this a little bit later, but I'm really fascinated by the history of this field because, as I was saying, scientists were trying for such a long time to really detect them. So, do you still remember the time when you saw the signal for the first time?
Sure,
it was there?
Sure. It was iconic, actually, in many, many ways. And it was also kind of surprising. As Sybil points out, the field of gravitational wave detections has a checkered history. There were several false claims all the way back to the 1960s, and even as recently as 2014 with the BICEP result on the cosmic gravitational wave background. So we wanted to be really ultra careful to check what was happening, and then we see the signal, and it's just so patently obvious that it's a gravitational wave. It was it was amazing.
Yeah, it was really a goosebumps moment, I think, for many people around the world. Well, now I would like to dive a little bit deeper into your current projects. Michael, it's perfect timing to have this discussion today because you just came back from South Africa, where you joined a meeting of the SKA for the first time with Germany as a member. So what kind of project is this? And so why is it so breathtaking and so exciting for the future of radio astronomy?
It's going to be the biggest telescope on Earth by a long mile, and it's going to be eventually a square kilometer in size. We're not there yet, far away from it quite yet, but it's going to be built in South Africa as one of the frequency ranges that we can look at in the sky, and one part is going to be in Western Australia. And it's an international project, which is at the moment 12 countries in the world and more to join. So it's a truly international project. And it's going to produce send images of the radio sky that has never been seen before. We expect that we can see every pulsar in the galaxy. The pulsar is my favorite object. So anyway, we can actually probe then to the very edges. We want to see how the first black holes were created, how the first stars were created, how they started to illuminate the universe from the universe started with a Big Bang, and then it cooled down, and there was nothing, essentially, apart from neutral hydrogen. But then the neutral hydrogen clumped together and formed the first stars. And then the universe lit up to the beautiful things we see today. And it's that transition that we try to understand, from the cosmic microwave background to the first stars, to the first black holes, how the first galaxies formed, how life eventually formed, because radio is also probably a very good way of looking for life. And so it's a huge endeavor. I'm personally working on this now for 20 years, some people even longer, and it's brilliant to see the first telescopes in South Africa, and it's also brilliant to have locations like South Africa being able to host this excellent telescope. So
we see it's similar questions again, but a telescope of a completely different scale. Again, combination of many telescopes. I always find this extremely impressive. Not just that it's on 2 different continents, but also the number of telescopes, right? So
yes.
It's so many telescopes. Do you have the numbers?
So in initial phase, are going to be about 200, but there will be many hundred dishes combined together. And on the antennas on Western Australia, there were about 100,000 of them that we combine.
So this will also mean a huge challenge regarding the data handling, right?
The same thing, yes.
And you're still developing everything, or is it already finished? Do you have an idea how to cope with all that data?
We have a design which is being implemented right now, and so the data will be better, mostly analyzed more or less on site. Then it will be sent with fibers to the partners in the world, where we continue to analyze the data continuously. But again, we're losing information because we cannot store everything. So we have to do massive data reduction in a literal sense and send the data. But even the storage is about an exabyte a year that we need. This is amazing.
Really impressive. But Linda, you were already talking a little bit about the ESO telescopes. So there are many of them in Chile, and they are extremely powerful. And so but I think many people still think that there's a kind of competition between Europe and other parts of the world. And now it seems like Europe really is at the forefront with its telescopes. So has Europe caught up, or even has it even reached the forefront compared to other countries? Or how's the situation of European astronomy?
So European astronomy is very interesting. I actually grew up in the US and did my PhD work in the US, and decided to come for an adventure in Europe after getting my PhD a long time ago, and never left. And I've seen how European astronomy has developed, and the one thing that Europe has learned is that projects of this enormous scale, Michael already sort of dealt with this a little bit, needs international cooperation. In a way, it was an advantage that any country in Europe was not big enough to conceive of something like the extremely large telescope, which is 39 meters, quite expensive. Technologically, it's unlike anything we've ever tried before. But the whole premise of ESO, the European Southern Observatory, was to form an intergovernmental organization, initially at 5 members, now at 16, all putting a large amount of their resources into ESO. And that made it possible. And such that even when one country might be experiencing some problems, the others compensate. And so it's an important lesson in international cooperation, and why international cooperation is so important to do things like basic research. Because it's not a given that any single government will provide funds to build something like the ELT. But at the end of the day, it's a reality. There's every month, I go to the ESO website every few weeks and look at the webcam, and you can see this thing being built in progress. And I was up at the site the last time a couple of years ago, and when you're inside this enormous dome, it's more than you can even imagine how this telescope is going to work. I mean, for example, one of the current ESO great telescopes, one of the 8-meter VLTs, can fit on one of the instrument platforms for the ELT. It's really amazing to watch. And this would not have been possible if the 16 member states didn't all collaborate, cooperate from the ground up, also regarding the instruments.
I think this is a very important point, especially in times like today, where international collaboration is becoming rather harder than easier. And I think astronomy and astrophysics is a very nice example to show the power of international collaboration. Frank, how's the European position, or how do you see it in terms of technological know-how?
Mm-hmm. Yeah, let me focus mainly on the, let's say, optical components that are required for the telescopes. I would say we are leading in Europe when it comes to high-end optics, and this is true for the mirrors, the large mirrors that are needed in the telescopes. It's also true, of course, for the refractive optics we are making. You can be pretty concrete here. We have, when it comes to fused silica, we have two players in the world who are able to make that material. One is in the US and us. So I would say we are leading in that field.
Okay, so now, David, you're the American here. After we have celebrated Europe so much, well, LIGO is an international collaboration as well. You also have European partners.
That is correct.
But the number of discoveries from LIGO and its partner observatories has been very impressive in recent years. So after the first gravitational wave signal, there came signals and new discoveries. So it was really impressive. So what's the current status of the project, and how is the search for gravitational waves going to continue?
Yeah, so we're actually running right now. We're in an observing run. Amazingly to me, we now detect gravitational waves mostly from colliding black holes once every 3 days or 4 days. I mean, people 20 years ago thought this was impossible, and now it's almost routine. Of course, it isn't. I want to actually come back and emphasize something you said, which is international cooperation is critical here. So I'm part of the LIGO scientific collaboration, but we work closely with the Virgo collaboration, which has an interferometer much like the LIGO interferometer. Theirs is in Italy. Actually, even here in Germany, there's the Geo 600 interferometer, which is not as sensitive. It doesn't really contribute to the astrophysical data, but it's been very, very important for prototyping some of the technology that we have been able to then adopt and bring into the LIGO detector. So that's critical. There's also a detector in Japan. So I think that's really, really quite important. I think the other thing to say, thinking, what's our ELT? So right now we're sort of in what we would call the first or second generation of these detectors. It's the same observatory, 4-kilometer arm lengths. We're starting to dream big, as are our colleagues in Europe, to build a next generation telescope, which instead of having 4-kilometer arms has 40-kilometer arm lengths. It's called Cosmic Explorer. In Europe, there's something called the Einstein telescope. So we're trying to move this field into a place where, the discovery space just opens up dramatically. And there are, so many things that we can't see with our current detectors that we think we will be able to see with these new detectors.
I talked to Barry Barish a few years ago. He got the Nobel Prize for the discovery, or for the first direct detection of a gravitational wave, together with Kip Thorne and Rainer Weiss. And he told me that he is very excited because he thinks that this new window of gravitational wave astronomy is going to show us completely new things and new physics. Yeah. Can you explain a little bit what he meant with that?
I think it already has. I mean, the other cooperation that we can do is sort of with the electromagnetic telescope. So the first binary neutron star event that we observed was observed not just in gravitational waves, but also in gamma rays and optical and X-ray, basically across the electromagnetic spectrum. And the amount of information, we learned so many things, like, for example, the collision of neutron stars produces short-hard gamma rays. That's been speculated for a long time. To Barry's point, what we can't do yet are, for example, measure very accurately the parameters of some of the collisions we see. So we'd like to be able to measure the radii of neutron stars, equations of state of neutron stars. We look at neutron stars quite differently from the way Michael does, in the sense that we can actually focus on one. If we know something about the neutron star, it's basically how fast it's spinning, its period. We can actually hone our algorithms to look and see if there are gravitational waves being emitted from them. So we can actually measure bumps on neutron stars that are the width of a human hair, all right, in our galaxy, close by in our galaxy. Should a supernova go off in our galaxy when we're online, we'll be able to look at sort of the last moments of the core collapse, as long as that supernova is spinning, and most of them do, so that we'll be able to take all of the data that you get from neutrinos, from optical, and combine it with gravitational waves to do this thing called multi-messenger astronomy. So we can also do cosmology. I mean, I could just keep going and going and going, but like I say, we don't have time.
Multi-messenger astronomy is a concept that we might explain as well, because I think this is one aspect that makes astrophysics so powerful, right? So can you explain a little bit what is meant by this?
Multi-messenger astronomy,
yes.
Yeah. The idea is that, if you're looking at one sector, and a sector is a messenger, in this case, would be a photon, and that photon could have different energies. It could be, as I said, a radio photon, an optical photon, an X-ray photon, a gamma ray photon. Just by looking at a source from just that perspective alone gives you a lot more information to basically extract the physics and the astrophysics from the source. Throw in gravitational waves, throw in neutrinos, and now, like I say, you're looking at complementary processes, so you can build a much more complete picture of the information that you can get from the source. So this binary neutron star collision that took place in 2017, which interestingly took place, I think, a week or so after the announcement of the Nobel Prize. So, gravitational waves got a big boost, from both the Nobel Prize and from this collision. Was you can just answer questions that you can't answer with one modality. You just can't.
What I always find fascinating is the question for the unexpected, right? And there was, there's a US astronomer, Martin Harwood, I don't know if you know him, so he also likes philosophy a lot, and he has this historical perspective, and he was once wondering whether astronomy could have the same fate as geography. Geography in the 15th and 16th century reached a point where basically everything was known on Earth. So all the phenomena were known and there were no fundamental new discoveries. So Michael, do you think that it could be the same with the universe at some point, that we basically know what's in there, and but then we have a deeper and deeper understanding, but we won't discover completely new things anymore?
No. No, the universe always surprises us. I mean, we have some good theories, some good understanding, and then there comes a new telescope, new parameter space, and we discover something completely unexpected. There are so many examples in history, whether it's pulsars or the cosmic microwave background. I mean, it had been speculated before that the Big Bang has happened, but the evidence was something where they even tried to clean the radio telescope from bird shit because they couldn't explain the signal. It turned out to be the signal from the remnant of the Big Bang. And so there are countless examples where the telescopes that were built for a special purpose discovered something completely different and unexpected. And it's that unexpected that throws us off, whether it's dark energy or dark matter. All these things were not expected, and yet astronomers found them with new telescopes, bigger telescopes, new parameter space. I think it's a very good idea of looking at this via this expanding of parameter space. I think we will always be surprised. We will never rest, and we always find some unexplained things, which then, as Linda said, throws up new questions, and so this will continue forever, I think. Well,
for me as a journalist, of course, it's really reassuring. So there will always be exciting news. We won't finish writing about astrophysics. So Linda, what does it take to make all these new discoveries, and how important is it to really look at the cosmos, with an open mind, so without too narrow expectations?
So what does it take? Technologically, it takes a strong collaboration between the astronomers and industry, as we've already touched base on that. There is no way that a telescope like the SKA or like LIGO or the Space Interferometer LISA or any of the ESO telescopes would have been possible without a strong collaboration between the people who are trying to develop the scientific ideas that they want to answer, and the people who can actually make them a reality. And in our institute, we do both, because we are building a lot of the instruments, and so we have a very tight collaboration with industry as well. And so I think that is the way to do it, is to think about the great question that you want, and then find a way technologically, working with the smartest engineers and physicists you can find, and then make it a reality. And I think ESO has been very, very, very good at doing that. And I mean, most of the biggest projects in astronomy have been very, very good at doing that.
So collaboration also with the industry, the big question. But of course, there's also another thing we need to have in mind. It costs a lot of money, right? So when
Yes.
I was a PhD student, when I was in Chile the first time, working at the telescopes, I was always extremely afraid that I could break something because I knew how expensive everything was. So it's often something like thousands, 10,000s of euros per observing hour.
Yeah.
So it's really
even more now with the new generation telescopes.
So if you think about this, it's a little bit scary. At the same time, it's really nice and good that we invest in these things. But still, there's always the question: why should we pay so much money in order to understand the universe?
So this was exactly the reason that I think that smaller countries there's no way, right? And so the only answer is you have to join forces with a large number of countries to be able to make it happen, such that the financial burden on any one given country is not astronomical. It is astronomy isn't a very expensive science, but the return that it brings to both in technology, but also just in inspiration. I think it's one of the sciences where if you take a 8 or a 9-year-old child and you bring them to a planetarium, they immediately are fascinated by science, and that fascination sticks. They will go on to do other things, probably, certainly not everyone is going to become an astronomer, but they will go on to say, okay, what could I discover now that I've seen how great the universe is? What could I discover in biology or in computer science or in developing new techniques to have more energy efficient buildings, whatever it is. I think astronomy plays an important role to show how fun science and development is. It's not just a job, it's a lot of fun, even though there's a lot of deadlines and a lot of pressure. And so I think that the return investment is worth it.
Well, probably, again, this is an argument, this is more important today than it has been ever, maybe, to really spread this fascination for science. And, I think that many people are interested in astrophysics and astronomy, even today when there are so many crises here on Earth, already speaks the language. Frank, what is your perspective from industry on that question?
Okay, let me make two examples, basically. Yeah? One is, we talked a lot about climate change during this conference, right? And for example, space-based telescopes are key to understand climate change, to do climate monitoring, Earth temperature, ice mass, forest cover, and so on. So that's one example I wanted to bring. The other one is more really industry and technology related. We were talking about large telescopes, right? Large telescopes require large optics. And we are developing these large optics. And these large optics are also used, for example, in equipment for chip manufacturing. So we are doing these large optics, nice homogeneity, and we can use them in telescopes, but also in industrial applications like chip manufacturing. So we shouldn't underestimate this spillover effect, if you will, of the technology itself.
Well, there's always a very nice example of that spillover effect from radio astronomy, right? So
that's right.
Do we have the same favorite example?
Some Dutch astronomers wanted to detect the evaporation of black holes. If they're tiny black holes and evaporate, they should produce a radio pulse. At least that was Martin Rees, astronomer royal in the UK, had predicted. But how do you find this? So some Australian working at the Dutch radio telescope designed an algorithm which every one of you has carrying with you right now, because it's the Wi-Fi algorithm. So the Wi-Fi example is one very good thing, where someone interested being in black holes actually has something produced that every one of you is using continuously. So that's just one example. The chip example is another good one. And so there are countless examples. And this is the reason why we're just building this new center in Saxony to combine the technology for astrophysics with the research and the instrumentation building in collaboration with the industry to have these spillover effects a bit more organized.
David, is it more complicated to get money for something as abstract and counterintuitive as gravitational waves? Would you say that?
I would say 40 years ago, yes. I would say now, no. To come back, like everybody on the panel here answered the question about what are the societal benefits, I think, quite well and eloquently. I don't know that I have a lot to add. But I will say that the reason we get support for these kind of, somewhat esoteric, quests that we are on is because there's a recognition that, science is the font of technology, is the font of economies, so you can make very general arguments saying you don't know where your next big discovery is going to come from. The example that I like is in condensed matter, there's something called nuclear magnetic resonance. If you're a physicist, you know what nuclear magnetic resonance is. When it was really being investigated in the 40s and 50s, no one predicted that it would turn into basically magnetic resonance imaging, MRI. So it's good to invest your money even in places that might not seem like they're going to give you a lot of applied technological benefit because you don't know where it's going to come from, right? And I think one of the things, just to sort of riff off Lindy here, that we do in LIGO is we train people, all right, in very complex technologies and very complex data analysis algorithms and things like that. And those people don't work for LIGO when they graduate. Sometimes they go off, they work for Google, they work for Apple, they work for Heraeus. So that kind of, sort of human resource development, at the cutting edge of the sort of the STEM, the tech frontier, I think that's a very important dividend that's worth investing money in.
So fascination, and we have the spillover effects and all the technological development, and we have the people and the education. Thank you so far. Now we have time for questions from the audience. Let's start in the first row. I think there are microphones somewhere.
Hi, is that on? Yeah. So I'm Eric Isaacs. I'm President Emeritus of the Carnegie Institution for Science. So I'm not representing everyone in the U.S., but we have a few people here also involved, like Chicago and the Giant Magellan Telescope and also the 30-meter telescope. But I have a question that I think is something that all of you can address, which is scaling up. So you've made a good case. Bigger is better. You get more resolution. You can look at exoplanets. You just can collect light better. You can look further away. More subtle features in the universe. Where is the upper limit of building earthbound telescopes? And this could be radio telescopes, it could be the mirrors for those telescopes, and it could be the extremely large telescopes. Even LIGO, you're talking about expanding it to 40 kilometers. That's to get the kind of accuracy you need at 40 kilometers. So it's a general question, but and it ties up to the cost, right? So we know that these ELTs are costing not just 5 or 10 times more. It scales almost quadratically, right, with size. It's not just a linear. So how do you think about earthbound telescopes? I believe they're very important, but where's the upper limit on it?
Thank you very much. Who wants to answer?
We have already telescopes in space. I mean, if you want to build a really big radio telescope, you can put it on the moon because you have less gravity, and so you can build bigger structures. And you have the advantage that you don't have the ionosphere, which blocks actually some of the radiation below 10 megahertz or so. In principle, I think humankind will always build bigger telescopes. At the moment, we are bound to Earth, but let's use that drive to be.
But then you're driving costs. So
You're driving costs, but I pass on that question.
You want to add something? Or?
No, I would also like to make a comment on that one. I mean, the biggest challenge for making optical components is at the end the combination of high performance, for example, low absorption, homogeneity, and so on, and bigger size. On the other hand, I have to say, if you would have asked me, I don't know, 20 years ago, would we be able to make these large optical components, like, for example, for chip making or so, I would have said no. So therefore, I don't think that we are at the limit when it comes to size of the mirrors or size of the refractive optics. But it's a question of cost, I agree. Mm-hmm. And the advantage we are currently having is that these large optics can also be used in other technologies, like chip manufacturing, for example. And then cost is okay still, at least for the optical part.
Let me try for the ground-based gravitational wave community. The next generation, these so-called cosmic explorer 40-kilometer, there's two components of them. There's the observatory itself, which is the infrastructure, and then there's the detector, which is the complex part of it. these detectors, including the Einstein telescope, are going to be designed basically to see the entire star-forming universe. So we'll get out to Z's of maybe 100 something like that. So it's unlikely that we would need to build something larger in terms of the observatory. What we will do, or will try to do, is to improve the way we detect displacements, how precisely we, and that those upgrades will cost some money. But in terms of sort of the observatory, the next ones are going to get us all the way to the edge of the universe.
One more sentence to answer for the ground-based optical telescopes. You probably know, ESO started off with something called the OWL telescope, an overwhelmingly large telescope, which wanted to be 100 meters. And cost, of course, came as the first thing. But at the time, the belief is that the things that's so important for these super large telescopes, which is the adaptive optics, to correct for the fact that we have an atmosphere, weren't going to work for such a big telescope. Whether that's still true in 40 or 50 years when we can afford the next step, I don't know. But I think right now, what we're currently building on both sides of the Atlantic, the planned telescopes, are probably at the fundamental both cost and technological limits that they...
So this was the bonus of the first question. Now we have to speed up. Yep. Next one was over there with the brown shirt.
Excuse me. Thank you. My name is Luan Sliwa. I'm a research assistant for the Max Planck Institute of Light. I have a question to Mr. David Reitze, maybe. So you told us that there's lots of sources for gravitational waves anywhere around us, really. And I would assume that the ones for terrestrial sources are probably neglectable, but there are lots of sources in the universe as well. So my question would be, how do you isolate the one source that you would like to observe? And additionally, how do you reduce noise effectively?
Yeah, it's a good and very complex question. In short, try and make it very, very short. So our detectors are designed sort of with certain frequency response from about 10 hertz to a few kilohertz. If you translate that into what kinds of masses that we can detect, in other words, accelerating masses, it comes out to stellar mass objects, one solar mass, maybe up to a few hundred solar masses. So the detections that we make are really limited in that mass band for binary collisions. How do we go to great pains to suppress noise, and you can write books about how much we do, but basically you got to get rid of the seismic noise, you have to get rid of the laser frequency noise, you have to work in a vacuum because basically molecules can introduce spurious signals and things like that. We use coincidence detection. We have multiple detectors. We know what these signals look like because you can calculate them using general relativity. And we use match filtering, so template-based searches. And then we look at the statistical confidence of that. And so there's a whole hierarchy of things that we do to get to a point where we can say this is a 20 solar mass black hole colliding with a 30 solar mass black hole.
Thank you. So I saw somebody over there on my right-hand side.
Hi, Kat Allman with Digital Science. General curiosity question, how is the field of astronomy dealing with the ever-increasing number of low Earth satellites? Is this an issue for you?
Absolutely, right. So it's an issue both for the optical and radio astronomy. It's a disaster, to be honest. No, seriously, I think we could be at a point where this generation, our children, were the last generation to see the night sky. It's because of the reflection of the sun that is constantly reflected from these low Earth orbiting satellites. But they also have emitting radio intentionally and a lot of non-intentional radio emission. We can see with our radio telescope, we see the onboard electronics of the Starlink satellites, and there's no regulations. So at one point, we will just be blind. So maybe we don't have to worry about earthbound telescopes anymore because we can't see the objects anymore. Because, it's a disaster. And the problem is that the international process of regulating, there are no international regulations actually. There's some UN committee where everything is on consensus, but no one is really bound by this. So, and the process is too slow. But maybe our grandchildren will not be able to see the sky anymore.
So one last question.
Thank you.
over there on the back, red pullover. No.
Hi,
jacket.
my name is Lyubov Pashavalo, United Nations Global Geodetic Center of Excellence. So the center works on implementation the UN resolution on global geodetic reference frame for sustainable development. And in particular, I work on conceptualization the robust global geodesy supply chain, which includes also, for instance, the VLBI observatories. And it's also important for terrestrial and celestial reference frame. So my question is, how do you see, what's the importance of the geodesy observatories for astronomy or astrometry and also satellite missions? And how do you see it evolving? And if you could put in geodetic stations or geodesy supply chain towards the context of the satellite missions, and if we could integrate it together. Thank you.
That's a complicated question.
Shall I say? I give a first step in that. It's hugely important. We need, as astronomers, we also need to know the exact location of the Earth's rotation axis. It's changing all the time. So we actually using the geodesy observation to correct our data afterwards, after the observations. But even the local reference frame, even this navigation on Earth needs all this geodesy information. So this is hugely important. So we need to keep this alive. We need to keep the frequencies alive to do these experiments.
You want to add something?
Yeah, not so important for ground-based gravitational wave. Our error boxes are measured in square degrees. So, but for other kinds of gravitational wave detection, perhaps pulsar timing arrays and things like that, it's the same argument goes. Michael just said.
Thank you. So I have a final one-word answer question, maybe. Well, this never works out, but I'll try anyway. So is there a potential discovery or result that you are most looking forward to and that you expect to tear down important walls in astrophysics? Michael?
I still want to find the pulse around the black hole in the center of the galaxy.
Thank you. Very good.
One sentence. We're looking at gravity in a completely, bizarre regime of, very high fields and very strong gravity and potentials. So we could actually start to see deviations from general relativity. I think it's a long shot, but that would be my go-to.
That's why I want to find this pulse.
That's right. So we're in competition.
In terms of time scales, what would you say?
Oh, that could be tomorrow. It could be forever. I mean, it's hard to know. General relativity is a really, really robust, bulletproof theory. So
We have to be patient. Linda?
The earliest stars, the earliest galaxies. And I think we will do it in the next 10 years by combining the very powerful space missions with the very powerful ground-based missions.
And do you think that there will be big surprises?
I don't know. I think there will be, because I think we never would have thought we would see early galaxies at a couple of hundred million years after the Big Bang, but we are. Yeah. And so we need to understand structure formation better, and I think there will be surprises.
Frank, I promised you not to ask you anything about astrophysics. Well, maybe...
I answer that question in a different way.
Okay.
So zero absorption fused silica. So to enable the big research projects will never come, but we work in that direction.
Okay.
Oh, I'm sorry to hear that.
So I think what we have learned today is that there are many exciting projects right now. So they either already exist or they are being built up. So there will be, huge new technological possibilities for astrophysics. And I think we can be pretty sure that there will be many discoveries ahead, many new questions, as Linda said. So stay tuned. There will be interesting things to see and to learn. Thank you to all of you, Linda Takuni, Michael Kramer, Frank Reitze, and David Reitze. No, last Demetrius. I get confused with the names. And Frank Street. Thank you very much for the vivid discussion. And thank you very much.